Dot product in space. Calculating the dot product of two vectors in space is similar to calculating the dot product of two vectors in a plane. As with vectors in a plane, non-zero vectors in space are perpendicular if and only if their dot product equals 0. Dot product and orthogonal vectors in space. The dot product of A equals A1, A2, A3, and B equals B1, B2, B3 is defined as A dot B equals A1B1 plus A2B2 plus A3B3. The vectors A and B are orthogonal if and only if A dot B equals 0. Dot product is a concept which you have earlier covered in the previous chapters. Example 1. Find the dot product of U and V, then determine if U and V are orthogonal. U equals -7, 3, -3. V equals 5, 17, 5. We will work out the dot product by multiplying -7 by 5, and 3 times 17 plus -3 and 5. And then we'll add the answers together. And this gives us -35 plus 51 and -15. And if you simplify this together, that's the same as 1. Since U dot V do not equal to 0, we can say U and V are not orthogonal. Try this question number 1. Please have a look at the question below and try to answer this particular question. It's very similar to example number 1, as you've seen earlier. When you have finished attempting your question, you can play this clip again. You are attempting try this question number 1, and it's time to share the answer with you. You had to find the dot product of U and V and then determine if U and V are orthogonal. The dot product of U and V is equal to 0. And because the dot product is equal to 0, we can say U and V are orthogonal. If you would like more help on attempting this question, you can watch example 1 again, and that will give you the detailed working out needed to answer this question. Angle between two vectors in space. As with vectors in a plane, if theta is the angle between non-zero vectors A and B, then cos theta equals A dot B divided by the magnitude of A times magnitude of B. Example 2. Find the angle theta between U and V to the nearest tenth of a degree if U equals 3, 2, -1 and V equals -4, 3, -2. We have introduced you to this formula cos theta equals U dot V divided by magnitude of U times magnitude of V. We will now use substitution to build this further. U dot V is 3, 2, -1 dot -4, 3, -2 divided by the magnitude of U, which is the magnitude of 3, 2, -1, and the magnitude of V, which is -4, 3, -2. This would give us -4 in the numerator, and it would give us root 14 times root 29 in the denominator. In your previous lessons, you have worked out dot products, and you've also worked out the magnitude of vectors. And this would simplify to theta equals inverse cosine of -4 divided by square root of 406, or about 101.5 degrees. The measure of the angle between U and V is about 101.5 degrees. Try this question number 2. You have to find the angle between U and V to the nearest tenth of a degree if U equals 4, 1, -3 and V equals -3, 1, -3. When you have worked out the angle theta, you can play this clip again. So here is the answer to try this question number 2. The answer is that the measure of the angle between U and V is about 95.2 degrees. If you would like more help to answer a question of a similar nature, you can watch example 2 again, where the details have been provided, and that should help you to answer this question more accurately.
Now, before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom. The first session is always free. We cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. So if you are interested in a free lesson, click the link in the description below and send us a message now. Okay, with that said, let's get back to our lesson.
Cross product. Another important product involving vectors in space is the cross product. Unlike the dot product, the cross product of two vectors A and B in space, denoted A cross B, and read A cross B, is a vector, not a scalar. The vector A cross B is perpendicular to the plane containing vectors A and B. If A equals A1I plus A2J plus A3K and V equals B1I plus B2J plus B3K, the cross product of A and B is the vector A cross B equals A2B3 minus A3B2I minus A1B3 minus A3B1 J plus A1B2 minus A2B1 K. If we apply the formula for calculating the determinant of a 3 by 3 matrix to the following determinant form involving I, J, K, and the components of A and B, we arrive at the same formula for A cross B. So A cross B equals, as you see in this diagram here, I, J, K. We have the components of A and B, A1, B1, A2, B2, A3, B3. And this would equal to the determinant of A2, A3, B2, B3, I, minus the determinant of A1, A3, B1, B3, J, plus the determinant of A1, A2, B1, B2, K. And this gives us A2, B3 minus A3, B2I minus A1, B3 minus A3, B1, J plus A1, B2 minus A2, B1, K, using the concepts of determinants. Example 3. You have to find the cross product of U, which equals to 3, -2, 1, and V equals -3, 3, 1. Then show that U cross V is orthogonal to both U and V. Firstly, u cross v would equal to, this diagram as you've seen previously, you'd have I, j, k. Then you would have your components of u, which are 3, negative 2, and 1. 3, negative 2, 1. And components of v, which would be negative 3, positive 3, 1. Negative 3, positive 3, 1. And this would be the same as this form here. You would have to work out the determinants shown in this particular step. And they would equal to negative 2 minus 3 I minus 3 subtract negative 3 j plus 9 minus 6 k. This would simplify to negative 5i minus 6j plus 3k. And that's the same as negative 5, negative 6, and 3. To show that u cross v is orthogonal to both u and v, find the dot product of u cross v with u and u cross v with v. U cross v dot u. That would be negative 5, negative 6, 3, dot 3, negative 2, 1. If we simplify this further, we have negative 5 times 3 plus negative 6 times negative 2 plus 3 times 1. And this would simplify to 0. Now we will work out u cross v dot v. U cross v, as we worked out previously, is negative 5, negative 6, 3 dot negative 3, 3, 1. This gives us negative 5 times negative 3, negative 6 times 3, and 3 times 1. If we simplify this further, this would give us 0. And because both dot products are 0, the vectors are orthogonal. Try this question number 3. After you've attempted this particular question, you can play this clip again. Here is the answer to try this question number 3. You were asked to work out u cross v to show that it is orthogonal to both u and v. So for the first part, u cross v gives you 9, negative 21, negative 6. Again, you can watch example number 3 again to find more details as to how we can work out this particular answer and the steps which are involved. And to show that u cross v is orthogonal to both u and v, we're going to work out u cross v dot u, and that gives us 0. We will also work out u cross v dot v, which also gives us 0. We can say, because both dot products are 0, the vectors are orthogonal. Again, please feel free to watch example 3 again if you would like to find the details and the steps involved in working these steps. Geometric application of cross product. The cross product of two vectors has several geometric applications. One is that the magnitude of u cross v represents the area of the parallelogram that has u and v as its adjacent sides. Example 4. Find the area of the parallelogram with adjacent sides u equals 2i plus 4j minus 3k and v equals I minus 5j plus 3k. First, you'd have to work out u cross v, which equals to ijk. Then you would have components of u, which are 2, 4, minus 3, and the components of v, which are 1, negative 5, and 3. This would equal to the determinant of 4, minus 3, minus 5, and 3, I, minus the determinant of 2, negative 3, 1, 3, j, plus the determinant of 2, 4, 1, negative 5, k. This would simplify to 12 minus 15i minus 6 minus negative 3j plus negative 10 minus 4k. If we tidy this up, we get negative 3i minus 9j minus 14k. U cross v equals to negative 3i minus 9j minus 14k, so we will use this to find the magnitude of u cross v. The magnitude of u cross v is the square root of negative 3 squared plus negative 9 squared plus negative 14 squared. And this gives us an answer of square root of 286, or about 16.9. So the area of the parallelogram is about 16.9 square units. Try this question number 4. Please have a look at this question and attempt to find the area of the parallelogram. When you have finished, you can play this clip again. Here is the answer to try this question number 4. The answer to this particular question is that the area of the parallelogram is about 23.3 square units. Please feel free to have a look at these steps, and if you would like more guidance, you can watch example number 4 again to help you get to this correct answer.